Good morning, everyone. Thanks for coming for the last deep seminar of the academic year. So before our summer break, today I have the pleasure to have Leonardo di Gaetano as a speaker. He not just, but a few months ago, he just finished his PhD in Vienna in higher interactions, and now he works in Marseille between neuroscience and theoretical physics. And then he is going to speak to us about the effect of higher interaction, structure calculation, and dynamic fluctuations of networks. Thanks for coming. Thanks for coming also last minute. It was a tough organization. And the floor is yours.
Thanks, Fernando. Thanks for the invitation. Actually, thanks everybody to be here. So yeah, as Fernando said, today I'm gonna work on what I've done during my PhD. Right now I'm working more on applications of like network science on brain networks, but today we're gonna talk about something that is not related to brain networks. So I don't know if everybody here is familiar about networks. I was asked maybe to do a presentation that is more broad for those that are not so familiar with networks. So just being quickly what networks are. So are mathematical structures, very abstract, that are used to study complex systems. So we use networks as systems in which we have nodes that represents the parts interactive of systems and links that connects these parts. This connection can be represent different things, such as like human interactions with respect to communications via social media or in person, can be used to model the diffusion of diseases and epidemic spreading, or also interactions in biological ecological systems, like in this way. Now, higher order networks are one of the generalization of simple networks. So this is the one, very illustrative visualization of a higher order network. So it's a network in which nodes can also be linked via group channels. So like in this case, we have links, but we also have 3-body interactions and 4-body interactions. Why this is helpful? Because like we have observed also from other sciences that real world systems, complex systems, they generally manifest group behaviors, such as the brain is known to have group mechanisms. So for wherever like we do a cognitive task, more parts of the brain, they communicate and work together to do a specific task, but in groups, not simply pairwise. Human interactions, so for instance, collaborations networks or team dynamics, groups dynamics, they involve group mechanism and coordination. We cannot simply understand how a group is working just with the dyadic interactions. And the same time, the same thing is also true for different types of human dynamics, such as, I don't know, conformism or other type of peer pressure, other social mechanism that actually happen in groups. So we hope that using a higher order network representation, it better encapture the real dynamics of these type of systems instead of the first order ones. So for instance, an example is that if we observe like our systems and we portray the system with a network. So imagine that like we observe a triangle or a triad of interactions. So if we use the higher order formalism, we can portray 2 different type of situations that wouldn't be possible otherwise. So with dyads, basically it's better to portray this situation. So we have 3 distinct people that are having 3 distinct conversations, meaning that also with respect to the data and let's say the qualitative information, we have 3 distinct topics that are argued in the conversation, but also these are happening at different times. So from a temporal point of view, 3 distinct dyadic interactions are different with respect to just one group conversation that is happening at the same time. So whenever like we have data that are temporal and are labeled with respect to topics or other metadata of interest, we should distinguish between these 2 things. So if we forget about higher order interactions, we're going to glue everything together and gluing together topics, the temporal properties, and so on. So in order to do this, like physicists and mathematicians have developed 2 types of mathematical structures to deal with complex systems that are slightly different, but are both useful. So the first one are the hypergraphs, and the second ones are the simplicial complexes. So hypergraphs are these type of structures, are nodes with associated a list of interactions. So the first order interactions are the so-called pairwise interactions. So dyads of nodes that interacts between themselves. And like this is a second order interaction. So a three-body interactions, a four-order interaction would be with, a third body interaction would be with four body and so on. While the simplicial complex is more or less the same structure, but with additional mathematical constraints. So, namely, that every time we have a simplex of a given order, so like in this case a triangle, we must include also all the subsimplices that form this simplex. Meaning that if we have a triangle, we should also include all the sides of the triangle, so the links. If, for instance, we have a tetrahedron, we should also include all the faces of the tetrahedron, so the triangles, and also the links that forms the triangle and so on. So simplicial complexes for, if you are asking, are better whenever like we have to apply things like algebraic topology on data, that is called topological data analysis, for instance, while hypergraphs are better whenever we want to define something that is more direct, intuitive for a physicist. So sometimes we have to define Laplacian for diffusion or master equation for differential equations, taking into account like group mechanisms. So in this case, it's better hypergraphs. And today we're mostly going to use hypergraphs instead of simplicial complexes. So this first work, it's an analytical work that allows us to treat generative process for higher order networks. So it's mostly analytical work. I don't want to go too much into details on the mathematical side, but more giving a general view of how this can be applied, also going beyond higher order networks. So I've done this work with my two supervisors of the PhD, Federico Battistone, that was my internal supervisor at Central European University, is actually one of the leading experts in higher order networks. So you can also check Federico's paper if you want to know more about the topic. And Michele, that was my co-supervisor, is also more on the computational social side. He has studied polarization, echo chambers. So it's more also an expert in human dynamics and social media. You can also check Michele's works out. So I would like to start doing a step back and starting from a more general problem that is a problem in complexity. So let's suppose that like we have our data, and in our data we observe something like patterns. It can be some properties that we want to understand if the property emerges from randomness or not. So there are two ways that we can face this problem to see if our observation is statistically valid. I asked ChatGPT to do two illustrations with my face to portray these two things, and the results is hilarious. So I prepare a slide on purpose. So I ask, okay, I would like an illustration to illustrate myself shuffling data ends by end, and this was the results. So actually, whenever like you want to compare like your data, you can do a bootstrapping, so shuffling your data and comparing your observation with a bootstrap analysis. So you shuffle all the data. I don't know why like the rest of water is flying. Maybe I don't know. I was portrayed as a magician by ChatGPT. But on the other hand, you can do something that is more exciting, such as generating a random network model and comparing your empirical network with your random network and seeing if the things that you observe empirically are the same things that might emerge from a random network configuration. Because sometimes, I mean, things can just emerge naturally from the random model that you use. So it's important to understand what are the properties that emerges from randomness also in network structures. So there are many models in terms of like random models that are used to compare empirical data with benchmarks, random benchmarks in networks. Two of them are, for instance, the Erdős-Sreni model and the configuration network model. For those that are not so familiar with these networks, they are basically the two go models to randomize networks. So the Erdős-Sreni has a fixed probability to generate links between every possible pairs of nodes, while the configuration networks basically is constructed fixing the starting degree distribution, the degree sequence, and then shuffling links. So we cut all the links, we shuffle them, and we glue them back. The idea is that even if we generate networks with random processes, they actually have intrinsic topological and temporal properties. So for instance, we know the clustering coefficient of the Erdo-Chauny and also the configuration networks are different. So this one depends on the average degree, and the clustering coefficient in the configuration network goes to 0. And also the percolation threshold, that depends on the average degree or the second momentum of the degree distribution, but in different ways. So these are two different type of random networks model, but they have an emergent different topological and temporal structure. So now let's suppose that we want to do something that is more complex, so generating more complex random networks model, even taking into account higher order interactions. So today we're gonna see what is the mathematical way to face the problem and like solve analytically like generative random process, also taking into account time and group interactions. So in order to do this, one can use the so-called hidden variable approach that was introduced more than 20 years ago by Bogugna and Pastor Sartorius as at the beginning for first order networks. So the idea is that we endow every node with a specific internal property that we call this hidden variable, and we assume that the connections of this random generative process exclusively depend on these internal variables. So this is like the idea. Now, this has been used in the last 20 years to generate a huge variety, a plethora of different type of models. So networks model that portray protein interactions, or networks that are embedded in geometrical or harmonic spaces, or even the very famous fitness model by Cardarelli that explains how human beings interact with respect to their personal fitness, is also a hidden variable model in a sense. So among all the possible models, we decided to focus on the activity-driven. The activity-driven model is one of the most famous, if not the most famous, temporal network model to explain like temporal patterns. It was introduced by Nicola Perra and collaborators in 2012, and then was also generalized by Giovanni Perri and Ambara in 2018 in the higher order version. So what is this activity-driven model? Basically, every node has a specific hidden variable internal property that in this case is the activity. So it's the probability that at every time the node is active, and whenever it's active, it fires to random neighbors links. In the higher order version, at every time step, it fires higher order interactions to randomly selected nodes. The cool thing is that if we iterate the process over time, we accumulate higher order interactions and links, and if we aggregate everything, like there is an emergent structure with specific properties. So today we're gonna apply this theory of hidden variable for higher order networks to this specific case. Now, activity-driven model can be used in different type of scenarios, actually being used in different type of systems, in particular for social systems. So there is this data sets portraying real face-to-face interactions with proximity data that is called social pattern, that has data set basically describing the interactions of human beings in conferences, schools, and hospitals. And many works have been done using the activity-driven model to study things such as temporal burstiness of human interaction, temporal patterns, and so on. So we also applied our research to understand temporal patterns also in this type of datasets, taking into account group interactions. So, okay, let's start from the topological properties of the network emerging from this type of dynamics. With topological properties, I mean, in this case, the degree distribution and the neighbors degree. So what's the expected degree distribution of the system, and also the expected correlation between my degree and the degree of the people that I know. So if there is a sortativity, meaning that high degree nodes are connected with high degree nodes, or this is sortativity, meaning that high degree nodes are connected with low degree nodes. So let's see what's emerging from the randomness of the model. So the theory in a nutshell, so just to give you a glimpse of what we do, is that we start from what we want to find, so the degree distribution of a given time t for a given order m. So this is an hyperdegree distribution. And we write that as a function of the original row, so the hidden variable or activity distribution, multiplied for this thing that is the propagator, namely the chance, the probability, to having an hyperdegree given a hidden variable. So this allows us to move from the starting distribution to the emergent degree distribution. For the model, one can find just with a bunch of mathematics that you can also find in supplemental material of the work, that the propagator has this Poisson form in which the average degree of the Poisson is given by this contribution that I want to show because intuitively show us what are the effect of the process. So we have that the expected degree of a node with a given activity is given by an outgoing term that is proportional to its activity. So the more it's active, the more the link that is gonna fire, but also he passively receives links from this mean field term that is the order multiplied by the average activity times the time. So why is this cool? Because it works for every order, like kinda well. So in this plot, I'm showing this is like the general formula. So we retrieve a formula that express the hyperdegree distribution as a function of rho. So the starting hidden variable distribution rescaled properly, rescaled with respect to time and also with respect to m, so the order. And if I plot the degree distribution times t over there is this rescaled quantity, the rescaled degree, I observe there is a collapse of our analytical prediction with respect to different orders. So dyadic interactions, three-body interactions, six-body interactions, and so on, it fits well. Also, we can find that this is the formula to predict the degree correlation. So the correlation between the degree of a node and the average degree of neighbors without the higher the interaction. So it depends on two momenta of the degree distribution, but also is proportional to the degree to the power of -1, meaning that there is a disassortativity. So this is also another emergent phenomenon that is not so trivial, meaning that from randomness, the system that we get it is assortative. So it has specific properties that, so for instance, if you observe from data that is an emergent disassortativity proportional to the k to the -1, this can simply be explained by randomness and not by some complex dynamics behind. Again, here I plot this rescaled quantity over k over t just to show that there is a collapse of the prediction also for different orders again.
Leo,
Yeah.
These are randomly generated hypergraphs.
Yeah,
this is coming from the social patterns.
No, in this case, these are synthetically generated, meaning that I took like a power law distribution from the beginning, and I feed them just to.
So you start with some activity distribution, and you have also some propagator. You use that to generate.
The propagator, I found the propagator analytically. I just started from this row that I said, okay, row is going to be a power law, and I generated this power law with the variables synthetically. The propagator, I know that has this form, so from the distribution, I calculated the average degree, and then I solved this. So row, actually, analytically, if you know that it's power law, you can put here a power law and fit in the data. That's what I did in this case. So I use this function, which gamma, for instance, in this simulation was 2.25 as a synthetic exponent of the power law.
I was going to ask, so to go to the expression where you express a big rule in the opposite. So am I to understand this correctly that it's saying at time t+1, I extract the probability distribution function given the distribution of time t-1?
No, the time is the same. This is still the same time. It's not a recursive equation over time. It's like given a time, so a snapshot of the process, even if like every time I increase the time step of the process, the network gets more connected. But given a fixed time, the degree distribution is written as the starting hidden variable distribution multiplied for this propagator that basically converts the probability distribution of the activity to the distribution of the degree.
That's the thing that has like the exponential form.
This row should be the power law. If we want a power law. In my case, in the plot that I show, I took row as a power law distribution. But you can also take empirical row, as I'm gonna show later, and you can also solve this for non-synthetic.
Yeah. So if I look at the +1 propagator that you have, and I imagine doing it at different heights, and then you have sort of a composition rule. maybe I'm focusing too much on word propagator. Just so I'm looking. So you have this plus one for time t. Right? Now let's say look at some different time. And then I apply it to time t minus one. Do I get a composition? Because it's also the way plus one propagator.
Yeah, actually, I mean, to find this for a fixed time, if you want to go more in mathematical details, you start from basically you say, okay, what's the probability? You want to understand what's the probability that a link exists at a given time t, and so you fix the time. You start from the chance that a link or a hyperlink exists, and from that you write then the average degree, the expected average degree. So you do that fixing the time, and you do that for every time.
That's like a percolation process.
Is the-
So
then the same
once
mathematic-
they exist, they stay there forever. And
Yeah.
you percolate through the hypergraph.
Yeah, that's the thing. Indeed, then we're gonna also apply the same formalism.
Propagator kind of like creates it's a propagator because it translates the activity to a
Degrees.
network at a certain time.
Yeah, that's the thing. So for just to be more precise, like the way I find the propagator is that, okay, I am interested in this quantity that is the average degree. How do I find it? To find that, I have to know what's the probability that a link exists. So if you go in the supplemental material of the work, you see that we start from the probability that a link does not exist at a specific time t. That is basically a binomial process because like all the hyperlinks are generated randomly, and like the more I go over time, the more it's unlikely that a link doesn't exist because there is always more chances to exist. So it accumulates probability over time, but then the solution that I give is for a fixed time. But I mean, we can go in mathematical details if you want more later. But still, the expression is found for a specific time t, not for two adjacent t. I'm sorry if I was not able to perfectly answer the question now. So
you're just is this
this is the degree correlation.
for simulated
Yeah.
okay.
So for activity distribution that are not empirical but are synthetic power laws, it works also equivalently with empirical distributions. Now, as was said here, yeah, we can apply the same formalism to study percolation because this is like a gathering process in which like the networks become more and more connected. We want to know when it gets to the percolation level. Means why percolation is important? Percolation is namely network science that face transition in which networks moves from a state in which is disconnected to a state in which is connected, fully connected, meaning that there is the emergence of a giant component. This is important because knowing the time of percolation gives us an upper bound for every dynamical process. So let's imagine that, like as in the first panel, we have the spreading of some dynamic process here as the red nodes. So if the nodes is not fully percolated, the red nodes cannot propagate over the whole network trivially. But if the network has already percolated, the process can spread over the whole network, meaning that if we don't have a percolated structure beneath, we cannot have the spreading over the whole network of epidemics, I don't know, diffusion process, misinformation, or whatever. So percolation is seen as a lower bound of every type of dynamical spreading on temporal networks. So how do we? Okay.
You put this percolation on a graph, or you also extend to percolation in hypergraph, so the hypergraphs emerge from the percolation in a graph.
No, this is like percolation on hypergraphs, meaning that we have a process in which we fire at every time step interactions of different orders. It can be second order, third order, first order, and then we see where the structure itself with group interactions percolates. So, for instance, I don't know, this is a structure with two order interactions, second order interactions in which like there are two components. Like I'm studying the percolation of this. So I don't know, for instance, I don't know this network. Where is it? This network like is fully percolated, taking into account different orders of interaction. So I'm studying this type of percolation. So nodes that are beginning and disconnected, and then I try to connect them via group interactions, and at a certain point the process is gonna percolate all at once.
I think I missed something earlier at the end. There
Is
is
the
the
order,
order of
yeah.
interaction. Okay, so you have a different degree distribution for every order.
Yeah,
And then what you're plotting here is, yeah, one for each degree.
yeah,
Yeah, like maybe we modify in the classic pairwise speculation, you have the giant component transition, and then you have one unique component. In your case, you are in a hypergraph. Your unique component is composed of any sort of hyper. It doesn't matter if it's only type 2, 3.
yeah. In this case, there's a case that I'm gonna show. I'm gonna solve the problem dividing the orders by layers. So I'm taking just second order, third order, first order separately, but I want to show what happens in terms of like predicting the percolation time, because the prediction can be wrong if we neglect the idea of using higher order interactions. That's the idea basically. But yeah, it's the same process, just taking into account group channels. So first,
So if you have like three nodes and then you have one or two buttons between them, then the system is percolated. I mean, in some sense, you consider that they are
Yeah.
all connected. So if you have very high order interaction, then the percolation is going to be easier.
yeah, should be faster. But okay, it's true, but there is actually something that is not that trivial that I'm gonna show afterwards for the application of this type of analytical prediction. So I mean, here I prepared a slide just to understand what's the mathematical way to approach the problem. I don't know if maybe it's so relevant, but basically the reasoning is that we start from a node and we suppose, okay, what's the probability that starting from this node and following one of its hyperlink, we end up to a dead end, so a point that is not gonna go to the giant component. In this way, we can write a recursive map in which the probability of not going to the giant component also should propagate to the adjacent link and also the adjacent link and so on. And so this is a recursive map over all the possible hyperlinks. We change the variable here. We define yk as 1 minus the probability of not belonging to a giant component. Close to the calculation threshold, this is basically close to 0. We can develop this expression in the first order, and we get this expression as a function of this matrix that is called branching matrix, that intuitively gives us all the possibility of the branches of the hypergraphs. This recursive equation can be solved just studying the spectrum of the matrix, in particular the dominant eigenvalue of the matrix, that is this form. Now, this form, in theory, is the same for every order, but depends on the hyper degree. But the dependence of the higher order degree with the variables actually changes with respect to the order. So putting everything together from the things that we found before, we found this formula that allows us to predict the percolation time of the higher order activity driven for every order m, given the activity distribution. Now, what's the thing? The thing is that, okay, it works well. We can predict still in the synthetic moment the percolation threshold. So here I'm showing the fraction of the nodes belonging to the giant component over time. And these peaks are the variance of the sides of the component. So when we have scale freeness in the phase transition, we have a peak. And the vertical lines are the predictions. It works well. And also the error in our prediction that is in this plot is scales as a power law whenever like we go to the thermodynamical limit of like infinite large networks. So the more we have large networks, the more accurate is our prediction. Now, why is it interesting from an empirical point of view? Because sometimes you want to gather data and then generating a random process that preserves some quantity. So let's suppose that we want to preserve the number of links over time whenever we project the network to the first order. So imagine that you have a data set, you imagine that the data set it's only first order, even if maybe there is a process that is with group interactions behind, and you just count the links over time. So here I have like two processes. One that is with group interactions, and the other one that is still random but is with dyadic interactions. If you count the links, here the sides of the triangles on top, or the links below, the number of links is always the same, so it is preserved. But in one case, we have a generative random process that is higher order, and the other one is first order. If we just project them to first order, they're going to have the same number of links. Now, do they have different temporal properties? So who's percolating first? In theory, we are thinking, okay, the higher order one is percolating first because they are group channels. Actually, the first order percolates first because, as you can see here, like there is no correlation anymore. There are no closed triangles, so the links can just go everywhere. And so we show this on empirical datasets. So we take activities from collaborators' datasets. So we take the datasets of people producing paper in the field of geology and history, and activities are basically the average rate of a scientist producing paper over a year in these two fields. Now, the blue dots, in which stars is geology and circles are history datasets, are the ratio between the prediction of the first order over the prediction of the higher order. And the more we increase the order, the larger is the error, meaning that, okay, if we just consider first order data, yeah, the predictions are similar, but then like it gets worse and worse. And the yellow dots are simply the prediction of our analytical solution with respect to the real empirical not the real empirical, but the simulated percolation time with the empirically gathered data. So our ability to predict the data is more or less constant, still close to 1. But the error that we do if we neglect higher order interactions gets higher, the higher is the order of interactions. Now, the theory is actually very complex. There is, we already published the paper like 1 year ago. If you check the paper out, there is gonna be an extensive supplemental material with like 30 pages of like mathematical derivation to find all the topological and temporal properties for not simply like the higher order networks that we use, so the activity model, but in general for hidden variables with higher order interaction. So if you're interested, you can check this out. As a second work, because I think maybe I'm running a bit out of time, it's already 30. Okay.
How this relates to other papers in our calculation, like the sleep calculation? How it relates?
Okay, so I've seen that in the last years, people have worked, especially the team of Ginesta Bianconi have worked on triadic percolation. That is another type of higher order percolation, meaning that there are processes in nature in which a node does not directly participate to the interactions of other two nodes, but it modulates the interaction. So for instance, we have 3 neurons in which like two neurons are connected and a third neuron is modulating with neural, I don't know, it's just modulating the process with neural receptors. So there is also another way to define percolation higher order in which the third node is not belonging to interaction, but simply modulates. So it affects the chance of creating a link. Now, I think that this theory can be used also for triadic works. I tried in these days to work just to try to solve models with triadic interactions via higher order hidden variable model. In theory, it's possible, but right now there are no works on this. So maybe it would be nice also to apply this to other type of percolation and generative process, such as like triadic models. Yeah, that could be actual direction.
So the data set
Uh-huh.
you use has interactions of mixed orders.
Yeah.
Or because I guess it's like a collaboration. We have mixed orders between 3, 4, 5.
Mhm.
But your random model is always a fixed order, right? Or do you also consider?
In this case, yeah, I consider like order by order because I wanted to see what's the error we do at every order. So for instance, okay, I have a data set in which I have papers that are done like pairwise and 3 authors, 4 authors, and so on. I just fix the order. So
also in order.
yeah, but then every time I project, the specific order to the first order, and I preserve the quantity of links that I would have at the first order, and then I generate that again as a first order, and I compare what happens. Yeah, but in principle, also you can do that taking into account all the orders together, and you can compute basically the percolation time also with all the orders together. But yeah, I did just with separate orders. Now, the second work is more on dynamical properties of higher order networks. In particular, I'm studying how higher order networks influence the rare events and the out of equilibrium dynamics of networks in general. So this work has been done still with Federico, but also with Francesco, that is an expert in large deviation theory, is a physicist, right now is a postdoctoral researcher at University of Nottingham. So if you are more interested in the theory of large deviation that I'm gonna explain now, you can also check Francesco's work. So even here, I want to start doing a step back, starting from rare events in nature. So what are rare events in nature? Let's suppose that you want to predict something like some real world behavior using some stochastic model. Now we know that even if we do the more complex model to predict, for instance, the stock market, taking into account machine learning, Markovian processes, and so on, something unexpected can happen, such as financial crisis. So this is a rare event, a catastrophic event in terms of financial time series. We can also try to predict with our, I don't know, multi-model synchronization, machine learning, whatever. We can try to predict the behavior of brain, but then something unexpected and catastrophic can happen, such as epileptic seizure. Other events in nature that can be studied with time series can also be unpredictable, such as earthquakes that basically are not predictable right now with our knowledge. And also, you can try to predict the sports outcomes, studying what are the data of a sport team and what are the way people interact, communicate, what is the efficiency of a team, but then something unexpected can happen, such as an Italian team losing 5-0 the Champions League final, or I also wanted to put the slide of Italy losing 3-0 with Norway, not qualifying for the third World Cup in a row, but it was too painful, so I just left this one. But still, besides the very, very sad jokes on football, physics and mathematics in general have already studied rare events in a more formal way. So here I'm showing 3 domains in which rare events have been studied. So in stochastic processes in general, rare events are the following things. So I'm going to give an example just to bring you to think in terms of rare events. So if we have a process such as tossing a coin, the expected event would be, okay, if I toss a coin n time, the coin is fair, the expected event would be to have tail half of the time. But thinking in terms of rare events is, okay, but what's the chance that tossing the coin 50 times every time I get tail? I mean, there is a chance, it's rare, but still there is a chance. So it would be also nice to know what's the probability of getting an unexpected event. In terms of physics, this has been studied in thermodynamics, knowing that given the specific temperature of a system, such as a gas, what's the expected energy? We know that by Boltzmann statistics, but also what's the probability that given the same microscopic state, so the observed temperature, the system beneath at the microscopic level is actually with a different energy, maybe an extreme energy, way more or way less than expected. In network science, this can also be applied to dynamical processes, so such as random walks. So we know that the expected time that a walker spends on a specific portion of the graph depends on the spectrum of the adjacency matrix, actually on the eigenvectors of the adjacency matrix. But we can also ask ourselves, what's the chance that a walker moving on the network spends way more time or way less time than expected on a specific portion? So in a stochastic process, this is still a chance. So we want to address this type of question. In particular, we want to address the question how higher order interactions affect this unexpected event on higher order dynamics. Why is this relevant? Because like we have seen in the last years that there are many works that study dynamical processes on higher order networks showing very cool and powerful results, but at the equilibrium. So such as explosive transition in social contagion with higher order interactions, or papers that studied the explosive synchronization in processes such as the higher order Kuramoto. So Kuramoto defined with group interactions on higher order networks. And also recently, stability of synchronization or the explosiveness of cooperations processing, game theory model in which we take into account group interactions.
Yeah, it's just, I think in particular the examples you had, so your definition of rareness kind of also depends on a time scale. Right? Because if you go back to your three examples, right, I can say all of them happen with certain, well, at least the first two, right? When you have the, so if you wait long enough, you will get n-tails, right? If you wait, if you wait long enough, you will almost certainly see, I think you mean even the entropy of all of these particles being in one point.
Yeah, of course, but
So at a given time, and then earthquakes, will certainly happen, right? Like a thousand year time scale, San Andreas faults have 4 or 5 to this. So that's not rare, depending on the time scale that you use. So I'm just trying to understand and maybe point out that your definition of rare also depends on resolution or like
it surely depends on the resolution, and like in thermodynamical limit, in theory there are no real rare events.
It's more precise definition that it's rare within a particular aspect.
Yeah, precisely. But also it has, given this, it has also an importance with respect to our ability to control and predict systems. Because if we do a simulation, generally we do a simulation for a specific and fixed time.
Yeah.
And so, we say this is the probability that I don't know, COVID propagates with this specific rate of infection and a specific scale of like 2 months, 3 months.
Sure.
But we generally show what's the expected value. But if we forget about the probability of having rare events, we forget about our ability to control the predictability of the model. So that's more or less the idea.
Yeah.
Of course, like starting to whatever system when time goes to infinite.
Well, the thing is, it doesn't have to go to infinity. That it can also. So there's what I'm saying that there's a combination of scales here that is at play that should be more precisely explainable. So time. So for example, this recurrence thing could happen very quickly if you had a small volume. Right?
Yeah.
So the thing is that there's a combination of scales that could be asking for a hierarchy in rather than that these are rare because they're almost certain if you change certain things. But this is all I'm trying to understand, right? So you can imagine in all these examples that the dynamics is fast enough, then for a shorter time scale, you're going to see all of these quote unquote rare events. So
yeah.
So it's really, so I'm just trying to understand, is this built into these discussions? Maybe not just with people. I'm asking more general.
No. This is surely more general. Actually, I prepared this slide just to prepare the audience of what's the type of thinking in terms of rare events with the random work.
Yeah.
Because generally people are either mathematicians or physicists, but they are not used to apply thermodynamics to study the dynamical properties of an event on a network such like this one. But of course, also as like the time scale affects like the use we make in terms of like pure thermodynamics, it also changes our prediction in terms of like dynamical properties of the network. So, but I think we're also gonna see now that what's gonna happen if we change the time scale of the random walk. So
there's 2 thermodynamic units, one large N and a large T.
Yeah.
In the coin flipping, those coincide because every time
it's the same,
do N, and then the rare events or the large deviations are going to tell you how your probability scales with that limit. That's the large N limit. Taking the thermodynamic limit, how's the probability of seeing a rare kill?
I'm gonna introduce in a while the large deviation principle. But so there is a plethora of cool works that show how higher order interactions affect the expected dynamics, such as phase transitions. This work is gonna be basically the first studying the effect of the outside of the equilibrium dynamics of a process. Among all the processes, we're gonna study the random walk on hypergraph. So what's the random walk on hypergraph? It was introduced by Timoteo Garnetti and collaborators in 2020. It tries to generalize the random walk on simple networks. So the random walk is this type of process in which we have an agent, or in the continuous case, infinite number of walkers that propagates over the networks, randomly selecting nodes. This can be used to study the diffusion in pairwise systems, such as the metropolitan system of a city in which connections are pairwise. Random walk on hypergraphs can be used to study the same type of diffusion, but over group channels. In particular, if in a simple network, at every time step the walker randomly select a neighbor, here it happens this. Just intuitively, the walker jumps over one of its hyperlink, and then among the nodes belonging to the hyperlink, he selects one of those nodes. Of course, in the limit of infinite number of walkers, averaging over all the walkers, it just spreads uniformly over the hyperlink.
It's like projecting the hyperlink. For example, if you have two hyperlinks that are both connecting node 1 and node 2, and then one is connecting node 2 and not connecting node 4, with the higher weights of transition from the thing, right?
This is precisely what you do. So to solve an analytically desired order work, you retrieve a matrix that is still a matrix, so it's not a tensor, it's not a order, it's pairwise, in which the weight to jumping from one node to another, so basically a link, is adjusted with respect to the size or the orders of all the hyperlinks between the two. So yeah, the trick is that you map this higher order process to a first order process, adjusting the weight with respect to the higher order properties. So yeah, you at the end study a transition matrix as you would do in the first order random walk, but adjusting the process. The point is that you can obtain this matrix starting from the incidence matrices, so the matrices that are nodes with respect to their link, to their higher order interactions. You multiply the incidence matrix, and you find this new transition matrix. Now, to solve this and studying the rare events in this specific process, we do two things. The first one is that we make use of the large deviation theory, and the second one that I'm going to introduce later is that we're going to build on purpose a toy model to control the structure. So what is large deviation theory in a nutshell? Large deviation theory relies on this large deviation principle, in which the probability of observing a specific physical observable eta with parameter n and t, observable t with parameters eta and n decays exponentially. And the decay, the exponential decay, is led by this term that is called rate function. Studying and knowing the rate function tell us to the first order was the way that the observable goes far away the typical state. So this is like the large deviation principle. In order to study what's the effect of higher order interaction to these rare events, we built a toy model in which we can tune the number of higher order interactions. So we construct a network in this way. We have a central node. We have a network that is fully connected with pairwise interactions, and we have non-overlapping triangles, second order interactions that always have in common the central node. So we can decide what's the number of these higher order interactions. Is very important because in this way we know precisely what are all the possible combinatorics, all the possible configuration, the number of configuration of the model that is going to be helpful in the future. As a physical observable, we consider what's the fraction of time that the walker spends on the central node at time n. So we want to observe how the rare events changes whenever we turn on or off the higher order interactions of the central nodes.
So small n is time,
Yeah.
and big N is the number of nodes.
Yeah.
Do you keep big N fixed, or you take
In this case, it's fixed, but also afterwards I'm gonna show that this works also for general configuration. Like the purpose of the toy model is that I also want to provide in the work, we provided an analytical way to solve that and to make the most fancy, elegant solution from an analytical point of view was also nice to compute the number of all possible configuration analytically, but you can also do that on empirical networks, making use of like brute force simulation and considering all the combinatorics numerically. But for the sake of showing an analytical solution, I'm presenting the results on a toy model. So the results on like rare events can be computed in two different physical scenarios. So the first one is the quenched case, and the second one is the nil case. What's the difference? So the quenched case, whenever like we're computing a physical quantity in a quenched scenario, we fix the structures beneath the dynamic, so we forget about the noise given by the structure, and we just observe the noise and the fluctuation of the dynamics. This is used in networks whenever like we want to study the dynamics on a well-known structure, so a fixed structure, or a structure that changing so slowly with respect to the time scale of the dynamical process that we can forget basically about this change and can consider that fixed. So at every time step, the structure is always the same, and I observe a different quantity over time. But if I don't know the structure, like most of the cases in network science, so for instance, I have noise, I have noisy data, I have, for instance, not a network, but a network that is generated by a stochastic process, so the one that we've seen in the first part of the seminar, or maybe we're working not on a network, but on an ensemble of possible networks that are generated by parameters such as, okay, the ensemble of network generated in the Erdős-Renyi case with specific P. So in all these cases, we have to use the annealed calculation, meaning that we have to consider both noise on the dynamics, but also on the structure, meaning that at every time step, we have to consider the observable, the physical observable, changing the network that we pick from the ensemble. So in this way, we do the average, mixing the noise coming from the structure and the dynamic. This is like the annealed case. Now, the results are going to be shown for both cases. But first, I want to like give you an idea on how to compute this in practice with analytical treatment. So generally, okay, rate function, so the exponential decay is not so easy to find. It can be found numerically if we run the simulation many times and we just check the tail of the distributions. But in practice can be found analytically doing a step back and starting from this quantity called scale cumulant generating function, that is the scaled expected value of this quantity, this exponential matrix, in which S, that was not defined yet, is like the tilting parameter that gives us like intuitively speaking, is like this contribution of temperature that is tilting the system out of the equilibrium. So the larger is S, the more is the tilt. Why are we interested about this quantity? Because we know there is a theorem that is the fundamental theorem in large deviation theory, the Gartner-Ellis theorem, that tells us that the rate function is nothing but the Legendre transformation of the scale cumulant generating function. So we have to find this in order to find the rate function, and then knowing everything about the rare events. Now, the cool thing is that in the case of random work and also other Markovian processes, since the process is Markovian, the rate function can be found simply, the scale cumulant generating function can be just found simply as the logarithm of the dominant eigenvalue of this matrix, this tilt matrix. So we just, a spectral analysis, we compute the logarithm of the dominant eigenvalue of the transition matrix tilted in a specific way, and we find the scale cumulant generating function. This is found for every parameter eta of our configuration. Like in our case, is the number of triangles of the central node. In the quench case, we just have to average all the possible configuration eta over the probability of having a specific number of higher order interactions. That's why we needed a toy model, because with a toy model, we know explicitly what is this P. that we can compute is like the probability of having a configuration with a specific number of triangles. So it can be 3 triangles, 2 triangles. In our case, the model was super trivial, no overlap, so the combinatoric was super easy. If you have a complex networks in which like you cannot describe analytically, you just have to compute this numerically from Markov chain simulation and so on. We did this in the supplemental material of the work to show that it works also on other type of distribution. So in the quench case, it's easy to find this and to find the rate functions. In the annealed case, the mathematics is a bit different. You cannot rely on this type of average because it's annealed, it's not quench anymore. So you can do this so-called saddle point approximation. So you start from the moment generating function that in the saddle point approximation can be written in this way to the first order. If I remind you again, what's the definition of this? The scaled common generating function is simply the scaled of the logarithm of this one. So just knowing the exponent of the saddle point we get doing again the Legendre transformation, what's the rate function for the annealed case. So it's very elegant, but it has also a caveat that we're gonna see afterwards. So what are the results? There are many results of the paper. I just want to show two plots that are the main results. So here I'm showing the rate functions in the quenched case, with respect to different densities of higher order interactions. So having a larger rate function, so going up, meaning that we have smaller fluctuations. So we have a more regular, a more predictable dynamic. As you can see, the more we increase the higher order interactions, the lower are the fluctuation of the observable of the time on the central node. So we can predict better what's the dynamic of the walker observing the behavior on the central node. You can actually find, if you use as an observable the peripheral node, that you have intuitively the opposed behavior in the peripheral node. So there is a behavior that is in contradiction in this, complementarily. In the annealed case, we find the same. But here, I mean, the plot is a bit different. So we observe two things. First of all, what's L? L is the annealing parameter. The annealing parameter is intuitively the rate in which like we change the structure beneath the dynamic. So when L goes to infinite, we have the thermodynamic limit of the anneal scenario. So the rate in which like we change the structure is so fast that is like the perfect annealing calculation. While when L is very low, like to 0 or 1, we retry again the quench case. So here, like in this rate function, we have the overlap between like the yellow line that is the annealed simulation with low annealing parameter and the quench case. So we get again the quench scenario. But when we go to the limit of the annealing parameter, we observe this plateau. So this plateau is not a phase transition. We were hoping this to be a phase transition. This was a matter of discussion for like 1 year in the rebuttal of the paper. This is actually just a mathematical artifact that is given by the saddle point approximation that we use, since we are approximating to the first order. What is interesting is that we don't care actually about the plateau, because we just want to know the external parts of the parabola, because this tells us the information about the out of equilibrium events for the most rare events, so the events that are far from the typical state. The center we have the typical states, but the out of equilibrium solutions are on the sides. So we are able to fit this solution. The straight line is like our analytical prediction, and the crosses are the numerical simulation with Monte Carlo simulation. So there is a good overlap between the two. And the simulation also works for intermediate value of the annealing parameter. Now, I actually didn't test enough that this theory, in my opinion, should go beyond the simple use of higher order interactions, because the large deviation theory in dynamical processes was not used so much to study other type of processes. In particular, there is still a huge gap in literature to study epidemic spreading or consensus or synchronization and so on. So if you are interested more in the technical part, this is also the work. I would like also to apply the same theory to study the controllability of dynamical and Markovian processes on network, maybe studying what other type of structures, not simply order interactions, affect our ability to predict rare events in dynamical processes. Now, to conclude, a future direction of the works presented in this seminar, I would like also to use maybe the higher order formalism to study other type of problems, not simply generative processes, such as the renormalization groups on network that was studied, making use of the hidden variable formalism also in the multi-scale approach from the group of Diego Garlaschelli, and I will also, as I said, using the reservation theory to other type of processes. If you are interested in simulating again this type of processes, I'm part of the library HGX, HyperGraphX, in which like you can find ways to use community detection and motifs for higher order networks, generative processes, simulate these dynamics that are shown here, and also ways to generate visualization of higher order structures. And that's it. These are the links if you're interested in the work. So thank you so much.
Okay, I have two questions. One is from this last on the admin version that you showed us. It was the last few. Yes, this is with high order. So those are like with like high order links.
Yeah, here the fraction of links is fixed, is p equals 0.5. So here, yeah, I'm not tuning. I already observed that increasing the density is also increasing the rate function. So here I'm asking, okay, let's fix that and let's change the any parameter. Yeah, in this case, yeah.
And then how does this change if you go back to the other one? So if you have three body, then it's more narrow, right? So there's less fluctuation, which makes in my head is I'm thinking, okay, if I have three body versus sampling randomly pairwise, then I will have a more modular type of network, because at the end of the day, you project your three body onto pairwise, right? If I understand correctly. So the analysis is done by projecting the three body interaction onto a pairwise network, and writing down everything as a pairwise network. But now the three body being sampled in a certain way.
I mean, I'm forgetting about the networks because then I just work on the transition matrix.
Exactly, but transition matrix
It's pairwise. It's pairwise, yeah, definitely.
So how would that change with respect to just saying I work with different pairwise process, but some are more clustered than others. Some I define my interaction to be more clustered than others, because I would have the impression that the three body interaction here will create links that are more local. Pairwise links that are more local because of the fact that they have triplets, right?
Definitely, they adjust the weight of triads, so they create like a clique with higher weight.
They create more cliques.
There is actually a work done by Francesco Coghi, my collaborator. You can check out. It was the first paper studying the random walk. They're applying large deviation theory on weighted the random walks. So that was the first thing. Like if you want to check the very first paper, and I think they also studied which structural properties, so like clustering coefficient and other things are connected with large deviation. So yeah, but in theory, that's like my point on the work. That's why I think that this shouldn't be just limited to higher order interactions, because in the moment that you are able to map your process, it can be higher order, multi-layer, whatever, to a transition matrix, you can apply that to everything you want, even like sign network, weighted network, or whatever.
Yeah, I think the difference is because in your case you're looking at random walks, and you can only jump from, you have to choose where you're going. But if you had like a dynamical process happening on the network, then you can have a difference between having a triplet versus having pairwise, because the way the process propagates may depend on the order of the instructions. That you may not be able to express this as a pairwise network. Because in this case, it feels like at the end of the day, you're studying a pairwise property. Just that they have different structures.
The mathematical framework, yeah, is basically the same. It's still a transition matrix that you build from a incidence higher order matrix, but at the end, yes, it's a transition matrix.
Yeah, last question. Let's thank